Well, thank you everyone for attending our latest Siemens seminar. Today we're going to be doing a seminar specific to working with CADCAM based programs. And in that topic, we will certainly get a chance to explore our Cycle 832 functionality, which is the high-speed mode that's in the Siemens 840 and 828 controls. I'm your presenter for the next hour, hour and a half, depending on how well we progress through the content. There's actually quite a bit of content here for us. Chris Pollock, I'm a dealer support specialist for the East Coast, and I'm here as a resource to you guys. So, down the road in the future, if you ever need any hand, have any questions on Siemens-based product, certainly feel free to reach out to me if I don't have the answer. And certainly I won't always have it. We have a large breadth of products, that's for sure. But send it out to me, and I'll be happy to help you guys out. So my contact information is here for you guys. All right. So upcoming events in the not-so-distant future, just to give you guys a heads up of what we have coming up next. I try to do these sessions. We strive to do them about every 6 weeks or so. The next one I have coming up, we're going to switch gears and segue back to turning and get a chance to explore some of the advanced turning cycles within the 808 or the 828 and the 840 control. So that's going to be coming up this December on the 11th. And then come January, I want to take a look at the DXF converter. So the Siemens controls have the ability of actually driving from a DXF file. There's an external piece of software you would use to be able to open up drawing files, DXF files, and then grab the specific content that you want and then save it in an MPF format so it can be opened up at the machine tool. So we're going to take a look at that whole process. It supports both milling and turning, so we'll get a chance. We'll probably look at the live examples in milling, but we'll certainly talk about the turning side of it as well. So that'll be coming up in January. Okay. So before we get into the base content, certainly for those on the call that maybe are new to this series or new to Siemens, I always like to get a chance to just show you our CNC for You website link. This is not only the link where you can find all of our webinars. Certainly we always like to have the most current coming up webinar posted on that, where you can register if you need to. But as well, this is where you can get to all of the previous webinars we've hosted and view any of that content. But besides the webinars, there's a whole lot of great information that you can find on CNC for You. So if you use that top link at www.usa.siemens.com/CNC for You, that'll bring you to our base landing page. There are links from that page where you can get to the webinars as well as a lot of other content. Or you can use the /CNC-webinars, and that'll just directly drive you right to that portion of that website that is specific to the webinars. So please remember, that's a great resource for you to continue to look for additional content on the Siemens product. So today's webinar, we're going to be concentrating on our 828, which would be our mid-range control, and our 840, which would be certainly our advanced control. Really, when you get to operation and programming, aside from getting maybe up into higher levels of technology, you'll find that segueing between the 828 and the 840 is, almost from a user standpoint, you don't even realize the transitions because they're so closely associated. They're both built on the same base software principle, what we call Operate. So anything we do here will apply directly into an 828 or an 840. And if there are any areas that are maybe slightly different, certainly point them out. But definitely in this topic, in this content, everything will transition between either platform. So anything we talk about today will apply to both of these control systems. So what are we talking about today? So this webinar, this CAD/CAM-based part programming in the high-speed webinar, what we wanted to do is I wanted to get a chance to kind of take an atypical job that you would post out of a CAD/CAM system and show you really just the overall process steps of how do I bring it into the system, how do we handle it, edit it, manage it, and then, even process it and run. And we're going to look at, first example, we're going to look at a Siemens posted program, and then we're going to get a look at a program that was posted in what the industry would call ISO format. A lot of us, are normally used to calling that Fanuc format. So we're going to really see the same job posted in two different ways, and we're going to go through some challenges, some areas for, to always keep an eye out, post development, structure, functionality, that kind of stuff. Once we've gone through the basic 2.5D examples between the two different modes or formats, then we're going to switch gears and look at freeform surfaces. So I have a nice, real simple little example of a freeformed three-dimensional cutter surface path that we will have machined, and we're going to start to look at maybe how do I handle that a little bit better. There's certainly some ideas that we can show you for managing more complex and certainly more cumbersome programs, and then we're going to apply the Cycle832 to that specific job, because that's really where you would start to leverage some kind of high-speed functionality, is more in what we consider, three-axis freeform type surfaces, although it could be used in 2D as well. So when we get through the whole process, I think everybody here will have a real solid understanding, really, of what it takes to program Siemens control externally and be able to manage it and utilize those functionalities at the control when it comes time to actually work on the system. So with that being said, the first area that we're going to start to explore and really delve into is what we call our G290 mode, or our Siemens mode. So a lot of people that run our systems, and it's just in this mode all the time, don't even realize they're in G290 mode, because if you're never switching between them, the system's just commissioned to be in this mode all the time. But technically, that's really what it is. It's our G290 mode. So as we start to switch between the modes, that would be the G code that could trigger us to be in the Siemens mode. So as we start to go through it, first thing we're going to get a chance to see is we have a nice little, just very basic 2.5D type of job program. I programmed it from Mastercam. We will get a chance to play around with Mastercam a little bit through this process, just to show you some of the triggers and play around a little bit with, just that whole process. So I didn't want to just limit it to static pre-programmed parts, so we can kind of go in and at least show you where some of these things would commonly link to an atypical CAD/CAM package. So this will be the job we methodized for both the Siemens mode and the ISO mode. From there, we're certainly going to go in and talk about how do I import the program, how do I manage it on multiple locations, whether it's a network drive per se, or USB, or some other external memory. Once we've found the program, we're going to talk about, managing it in this program manager area, some of the key functions. If I want to create directories or move around, certainly we won't be building new programs, but, opening and editing these programs. From there, we're going to go into the editor, and we're going to show you what a typical posted program out of a CAM system would look like. So we can get a chance to go through the structure a little bit, what I would expect to see when I start to work with these externally posted programs. From there, we're going to start to talk about maybe some challenges or some issues that would be commonly faced when dealing with working with CAD/CAM, specifically from the post-processor side of the world. Post-processors are always a challenge because it's a piece of software, certainly held and owned by the CAD/CAM manufacturer, that takes their code or their internal process, and it's a translator, right, to translate it into a machine tool language. And certainly there's an interpretation when somebody develops this post as to how the machine wants to see this stuff. And there are some common scenarios that can be little challenges. Those are the areas we're going to concentrate and look at a little bit today. Excuse me. So we'll start to explore that. And then the next step certainly is how do we then support these CAD/CAM posted programs from our offset table. Setup may be a little differently depending on how the file is posted out. So we'll explore some of those avenues of setting up the tool table, setting it up for common tools that I would see coming in from a CAD/CAM based program. Once we get through that process step, we'll certainly start to simulate it play around with utilizing the built-in simulation in the control to kind of see what's going to happen and what's going to go on in this job to get us a good understanding of what's going to happen before I actually go and run the part program. Okay, so this is always the point in my presentations where I like to really get away from these static PowerPoint slides and start to talk about and work on some live demo portions. So if we come in, we're going to launch our SINUTrain software. This is the software we use. It's a PC-based software. That's a machine tool emulator. So this is really going to allow us to do everything we would do on a physical machine tool without having to worry about having a machine tool hooked up at this point in time. So the machine we're using for our example today is a 4-axis machine. So we see that we have our 3 linear axes up in our upper left-hand corner. As well, we have a rotary axis. Now, we're not going to do any rotary axis specifically on this part, but certainly, you know, we could if we wanted to. We could be posting 4-axis jobs quite as well as we're posting 3-axis stuff. So from here, you know, when we talk about managing programs and dealing with programs, the first thing when dealing with getting programs in and out, we have to get used to is the program manager. And, you know, for any of us that have been doing any level of part programming already on the control, this is all very familiar to us. It's the same exact area where I would normally go in to do basic part programming. But usually what happens is once somebody starts to work with external programs, they now have to bring things in from an external source. So that's kind of where people you may maybe not have used some of this functionality to bring stuff in and explore different areas. So certainly the easiest and the simplest would be working with a USB port. So the USB port is generally right there on your front panel of your machine. So when you post out a given file, you can save it to a USB, come over. Once you plug it in, the USB will go black, and then it's going to look like any standard file structure. And then you're going to simply use your cut, copy, and paste to take the file and move it over maybe to some local drive area, so you don't necessarily have to be relying on driving it from that USB stick. Now, you can run from the USB if you wish to, but we tend to recommend, especially with USBs, because the connections aren't that great and the device itself don't tend to be the most stable of devices. We usually do recommend that if you're going to run programs, you most likely run them from a little bit more stable memory, but you can if you wanted to run from USB. So normally what you would do is you'd copy and paste the program into either the NC directory, and NC is our certainly our program work area. This is our active memory in the control. And you can also have, if you have the option, a local drive. And the local drive is here as an extended memory. Now, this is still specific on the control, but you do need to have that option to have the local drive feature. And then you can run, edit part programs from either source. It really doesn't make any difference how or where you handle them from. And you're just going to use, again, the cut, copy, paste commands to move these things around. The other area that's really nice to set up when you start working with external posted programs would be network drives. And the way a network drive would work is obviously you'd have the system networked into your machine, and then your network administrator would assign you some shared folder. And the shared folder would be mapped on the control, and you'll get a soft key here somewhere on the side of the screen on the horizontal soft keys, and that will represent whatever map directories I happen to have set up. So in my case, since this is actually just a PC, what I did was I just mapped external folders on the PC for me to kind of get outside of SINUTrain to a specific folder. But the mechanism will be the exact same way as if you were handling this from a network drive. So if I wanted to start, you know, playing around with the system and working on these files, I can just access my given network drive. It's going to look very similar to like a Windows folder type format, and I can expand and contract different folders as I need to, drilling into wherever this program or this mapped network drive happens to be. Now, when you're using files sitting on a network drive, you can run, edit, anything you want to do from those, or you can copy them into NC memory. It's really kind of up to you and how you want to process it. I have a lot of customers that leave things specifically right on the network. They don't even bring them over. They run them right from there. So that's certainly an option that you can do. So if we want to take a look at it, what I have here is I have just a very atypical posted CADCAM file. So if I come in and we open up a program. In this case, we called it G291_M_CAM. This would be a posted file. Now, probably the first thing to note and to make mention of is the extension on the file name. So whenever posting or creating files, if it's going to be a main program, it will have a .mpf extension. So if you look back here, see how the file of type says MPF, stands for main program file. So all CAD/CAM postal files will have an MPF extension. So if the system wants to post it with anything else, and that would be a nature of the post processor, where you can have a post processor set up what the extension is. A lot of them just post as a text format. Just make sure you rename the file as an MPF. If not, if you were to do the process of saving the file over to NC, it'll tell you that it doesn't recognize or support that file extension. It gives you the opportunity of renaming it at that point. But if you want to run from an external source, you certainly have to make sure that the file is already set up with the correct extension to be able to use. So this would be typically how we would see a Siemens posted file, this G290 mode file, looking. So in our world, we use semicolons for any comments. So, usually in posted programs, you're going to get some user notes at the very top, materials, file name, dates and times possibly, a list of the tool library or the tools we'll be using for this job. So in this example, we see that we have 4 tools selected. There's 4 operations in the job. And then we kind of build it from there. And then we can scroll down and start to see some of the common features and common commands. Let me get rid of this for a sec because we're going to put that in later. Some of the common commands that you would see posted out. So first and foremost, a lot of the times when we start to look at tools coming out of a CAD/CAM system, most CAD/CAM systems aren't necessarily set up to support our naming terminology. So in Siemens, certainly if you've attended some of these seminars with me before, you'll have seen that we can call a tool a half-inch end mill, 3/4-inch end mill, face mill, whatever you want to call it. And that would be the name that gets called up in the program. However, if a CAD/CAM post isn't set up to drive those names, you're going to end up with numbers. So it'll be tool 1, tool 2, tool 3, and there's absolutely no problem with that. The system can handle it. You'll just have to know that you'll have to set up the tooling specific to that. So in this case, we see that tool 1 is a 3/4-inch end mill, and then we go up from there from tool 2 to tool 3 to tool 4. So when we segue over to the offset table to set this job up to actually run so we can start to simulate it, we'll just need to validate that these tools are set up for this protocol. So if we segue there, we can hit the offset button and start to see our tool table and how it would look. So here's an example of the traditional creating, or our traditional creating a tool with a given name. So in the G code, it would look like T equals, and then in quotation marks, this 3/8-inch end mill. But since that program was written with numbers, what happens is you have to go in and physically just type the number for the name. So I've pre-set up these 4 tools right here. You can see them in a couple different locations. But really, the way you would have done it is just find an empty spot or go to our unloaded section. This is all the same as we've covered in some of the earlier webinars. But I would do a new tool, find the tool type, and then here in the name, I would give it a number, and that number needs to obviously correlate to the number in the program. So if I knew I was creating number 6, I could put it here. Now, I do get a lot of guys ask me, can we put comments or notes in the tool name? Because, certainly with this, since it doesn't have a real name, I'm kind of losing the ability of knowing what that tool was. I have to look at the size and everything to determine what size cutter it is. Unfortunately, you cannot. If you put a semicolon in now and type some name, it's going to treat everything in this field as the name of the tool. So then that would have to have been reflected in the part program. So when you do use the numbers as the tool names, you're only allowed to put just the number, or it would have to match the physical entire string that would be in the part program. Okay, so here I have a tool 6. We define some length. This certainly will be created when we touch off the tool. Whether it's CAD/CAM, you can use positive tool length offsets. That's really just up to you as to how you want to set up the machine. But here I would stipulate whatever diameter the cutter is, Now, when working with posted files, generally you're going to find that the majority of post-process are just going to support, from a milling side, feed per minute. So with that being said, the number of flutes field here has absolutely no bearing on the part program. You can certainly put it there for your own reference, but if you're only ever in G94 or feed per minute mode, it's never going to look at this field, where normally this would be my number of flutes. Now, G-code, we certainly have the capability of programming feed per tooth, so you can take advantage of it, and then the system would look here to determine its feed rate, but typically you won't see that out of most post processors. So again, this would just become a field for your reference. The same thing holds true for our direction. When we're working in G-code based programs, the spindle direction and the state of the spindle, whether on or off, will be driven by M codes, M3, M4, M5. So with that being said, you can put anything you want here. The system's never going to look at it. When it will, however, look at it is in shop mill or conversational-based programs. So if you're creating a tool that's going to be potentially used, between shop mill programs and CADCAM programs, then you would want to pay a little more attention for this when it gets used for a shop mill-based program. And same holds true for your coolant states. If you turn coolant on here, it's not going to turn on just because you loaded a tool in G-code. It has to drive from its associated M code, traditionally an M8 for flood, M9 for coolant off. So these coolant commands as well don't have really any bearing generally when you deal with CAD-CAM based programs. But then from there, you can start to build up your tools. Now, when it comes to drills, I still build them as a drill, especially if I'm in our Siemens mode, because our CAN cycles will still support the ability of compensating for tool tip angles and whatnot. So if you didn't have the tool defined correctly here, then it wouldn't know how to support that. But if the system isn't taking advantage of any of those features, then as well, those become not necessary fields of input. But if you are posting in ours, and they're utilizing this functionality, and we'll see that in a little bit when we go to the CAN cycle, then you would want to give it the appropriate tool angle here. So now when we transition back into our part program, we now have some tools we can potentially simulate and see if what I gave it is at least starting to run and function. So when I look at it here, when I first start to run, we see just the cutter kind of spinning around. I'm going to do a quick little auto zoom, but we have nothing on the screen other than a tool bouncing around. So when we first come in and we first start simulating CAM-based programs, if there is no block form, and block form is what sets up our 3D graphics, then you're just going to see the tool kind of moving around the screen the way you saw it. One of the simplest things you can do to start to get some acknowledgement is by turning on the show path function. Show path will at least give us a wireframe of what's about to happen. Now this wireframe is derived from the center of the cutter, so it's not exactly a perfect representation of the part. It's really showing you your actual tool path. But if that's all we're worried about, this gives us a pretty good understanding of what's about to happen based on this part program. So we can certainly manipulate it and look at it the way we would on other geometries. But if we want to start to get a little bit better of a conceptual and we want to see the 3D model, then there's two ways we can get that to start to work. The first, if I'm working with a system and I don't want to edit the part program, I don't want to edit the G-code, you can use this blank function to turn on the block form. Now, the downfall is you have to let it run through one full cycle of the program before this blank becomes active, because while it's running, you'll see the blank is grayed out. So we do need to let it go through one scenario. Once it's done, however, you'll see the blank will become active. And once that happens, I will now have the ability of inputting just like I would have if I was free-form programming. I have all the same variables, pipe, cylinders, block center, any of those standard variables. But now when I fill out this page, it's going to give me my block form. So if we simulate it at this point, now we'll see a real cutter come down, machine out the part as we normally would. So that's usually the quickest and simplest way to start to get the graphics to become active when we're dealing with CAD/CAM-based programs. But however, the downfall, the limitation here is every time I leave, I make some editing change, and then I want to go back into simulation, we're going to have to return on the block form. So I come in, it's going to come in, it's going to start. I have to shut it off or let it run to completion, accept the blank, and then run. So there's a couple extra added steps. Now, obviously, if I'm in a scenario where the part programs have been locked down, certainly any programs that had to be validated or approved, sometimes you can't edit at all at any type of functionality, even if it was for graphic support, then this would be the only way we could turn it on. But if we're allowed to do some basic editing at the part program level, then what I would do is I would add, and that was actually what I deleted real quick before, because I had added it earlier, but what I would do is I would add the block form here. Now, where would I typically like to see the block? Certainly very early on in the part program, certainly before it starts to cut any real geometry, but where you want to have it is you want to have it just after the work coordinate gets called up, right? So this is the fixture, that's the work coordinate that we're going to be using, our G54 through whatever. We support up to 99, but you can be using any of them. So this would be work coordinate number 1. So I want my block form to be after that. If I have it before this, then you might find a scenario where it appears to be machining not on the block form, and that's really because it's applying the numbers to the work coordinate level after it builds the blank. So if I just get in the habit of always setting up my blank after my work coordinate, then I won't get into that trouble. So if we go over and we go to various and we jump over to blank, this is where we would have normally inserted it if we were longhand programming. So it's the same scenario. Come in, fill out the page to the appropriate dimensions of the blank. In this case, this part happens to be set up with the center being 0, 0. So I just gave it a basic width, basic length, top of the part, overall thickness of the part. I accept it, and it inserts the blank block form for me. Now, can you get your CAD/CAM system to output this? Absolutely. I've worked with plenty of post processors, Mastercam included, that has the ability to output this block form and drive it from their own internal graphics. But this is a function of the post processor, so it really is up to your post processor developer to be able to support this this blank form here. Okay, so once I plug it in, then now it's going to drive and kind of react like any of our normal systems would. So we come back, and we can now start to see our standard simulation. So we were talking earlier about working in the system, maybe some differences within the Siemens control, and specifically challenges when you get to dealing with common issues that you might find in post processors. And in this side, I would say probably one of the biggest ones is dealing with CAN cycles. CAN cycles, specifically drilling cycles. So if I scroll down through the part program, I get to tool 3, there's my spot drill or my center drill. And you come on down a little bit further, and now you're going to see our CAN cycle. And this would be a traditional CAN cycle in a Siemens world. And a lot of times this is kind of what stumbles guys. Those of us that are more familiar with the Fanuc or ISO side of the world are used to axis designators on every single variable instead of this comma delimited type of string. Well, the reason why we don't have any of these axis variables is because all of our cycles automatically have, and when I hit the blue arrow over, I can open them up, a conversational cycle support. So here I am posting out of a CAD/CAM system, but I can still edit it conversationally at the control. And that's why we don't see it. Now, normally what I find here, and this is a common scenario, is that if there's any issues with a guy setting up a post, a lot of times, probably one of the first most common scenario is they're just building the CAN cycles incorrectly. So what I would always suggest when you're first kind of validating the post you're going to use, push a few of these variables down through, open up the cycle and the mask, and see if it makes sense. Is my retract equal to or greater than my safety distance? And that's a pretty common scenario. This is where I'm going to. This is how close I'm going to get. did they fill them out? Are things blank that should have been filled out? You know, is this really being fed from the top of my part field, or is this coming from some other field? Now, we were talking about the, supporting the tip angles. Certainly, if they've put provisions in to support it, the system can even derive some of these advanced features that would use the tip angles from the tools. But it really is up to the post developer how far he wants to go and how much of this functionality he's intending to support here. But that's really where you can start to see if there are issues, and probably more of the most common areas where you will stumble into some issues is, you come into here and you'll see some kind of scenarios. Now, in this case, this was a modal drilling. That's what your MQual has here. So we're doing 2 holes, as we saw in the simulated pattern, and then shutting our drilling off with the additional MQual. So all this stuff was driven from the CAM system. So if we wanted to kind of see how some of this stuff interreacts with a CADCAM system, I do have MasterCam here. This is what I was using to post this program. So what we can do is we can kind of play around with this a little bit, and you can start to see how you can, kind of force different variables and see what the resulting outcome is going to be. So what I'm doing here is I have 4 operations. This would be using our Siemens side of the system. And if I go into my drilling cycle, I can get down and drill into the CAN cycle portion of this cycle. So in this case, the guy that developed this post did a very nice job. They're even showing us cycle 81, 82. They're giving us the cycle name. These would be some of the additional fields supported. And then it's also being driven from the basic depth, top stock, bottom stock type of scenario. So here we can start to maybe play around and see how are they feeding and how are they driving some of these values. So for argument's sake, if I come in and maybe change a retract value to 100 thou, or maybe change a depth to -0.2, excuse me, we can save it. I can post it out, and we can start to look at it at the control. And then you can kind of decipher whether you have some posting issues that you may need to address. So I'm just going to post out this simple drilling operation. I'm going to create a little, I'm going to use a little program here called sample that I'm just going to use to kind of keep overriding. So what we've done is what I did was I posted it directly to my shared folder. So that's where my sample. And the same scenario kind of will hold true for you guys. If you're using a network drive, just post it right to the network drive. This way, then from the machine, you can commonly go and grab it. So in this case, I come down, I open up the cycle. Now, before we had 0.2 here, so right off the bat, I now start to see, well, whoever developed this post has the retract plane and the safety plane being driven by the same field. And that actually could be a problem, because if I need to use the retract to get up and over something like a clamp, it's always going to be this small value. Or if I put in a large value, the safety goes with it. So now all of a sudden it's feeding from some huge number. So this is where you can start to determine if a post is working, working correctly or not. Areas where guys have a tendency to maybe shortchange it would be when you get to like absolute incremental scenarios. Physically in the CAN cycle, a lot of times we have the ability of programming depths absolute or incremental. Now this one certainly lets me do both. But if I come in and I switch it to incremental, we save it. Let's rebuild it here. And we'll post it out again. And we'll just write over this save one. Now when we go in and we go to edit this file, we open up our cycle. I see that my trigger is still absolute. So here, he's not taking advantage of the absolute incremental trigger switch at that. Then from here, is this functionality that you need or not? And if it is functionality you need, then you'd have to push it back to whoever did the post development for them to support or fix these functions. Sometimes it's not always a case of just finding issues with the post as much as it's a case where I just need to find out where the limitations of that post are. And then if they're not anything that's going to affect what I'm doing on a day-to-day, you can leave them. You just want to be aware of them, because the last thing you want to do is start pushing things through to the control that aren't really being translated properly, and then you're going to drive yourself absolutely crazy trying to chase these issues. Okay, so that's dealing with certainly with some drilling cycles and whatnot. I am going to now segue over to some milling features. So if we go back and we take a look at our program, quite commonly we like to output cutter comp, and there are two different ways to output cutter comp out of a CAD-CAM system. You can output it where this is what I'm talking about here is when we're physically getting cutter comp being posted to G41 or 42. We can do what's called full cutter comp, or cutter comp where the control is handling it, the machine tool is handling it. So this would be an example of this scenario. So in this case, the output code would be output without compensating any tool, and then we are putting a G41 out. And now that's going to give us a resulting cutter path that's using the full tool diameter of the tool table. So in this case, we're going to get the exact same scenario that we saw before. However, if you notice the lead in, lead out, it looks a little funny. Sometimes CAD-CAM systems have a hard time anticipating and handling the lead in and lead outs in this scenario because they're not really sure what tool diameter you're going to end up with. I could start to change this entirely. This gives me a lot of freedom. So now I'm not limited to just using, a 750 tool. Oh, I'm on the wrong tool. Sorry. I'm going to be on tool 1. The 3/4 inch tool, maybe I wanted to use a 1/4 inch tool. Well, now the program itself can accommodate any full range of tools because we're doing the full cutter compensation here at the control. So I'm still ending with the same results. My end profile is supposed to be 4 by 4. And if I kind of look at these little hash marks, I can see I'm still ending up with a width and a length of 4 inches by 4 inches. That's because we're using the full cutter compensation. Now, this is where it gets a little tricky. Probably I would say the most common type of cutter comp isn't full cutter comp, but guys will use what's called comp wear. So if we jump back to Mastercam really quickly, and we go into our parameters section, and we go to our contour, if you look at the compensation type, we have the computer, so that's giving you a comp path, but there's no G41 or 42 being output. You have control, that's saying the machine tool will handle it. That was the scenario you just saw, but then you may have some issues with your lead in and lead outs. Or you can use wear, and wear I would say is probably the most common of all the strategies leveraged. So what is happening with wear? Well, the output path out of the system here is compensating for this tool. So in this case, it's a 3/4 inch end mill. So the path is off of the part by 3/8, by the radius of the tool. But it's also still outputting a cutter comp statement. So if I need to adjust this path out or in to accommodate for wear or inaccuracy in my grind, I would use a small incremental value. This is the problem. When you do that, right, so here's a profile with wear. When you do that, you get double compensation. So let me just comment out this line real quick because we're going to get back to it in a sec. So when I simulate it, the control has no idea that the cutter path was already compensated. And let me put the big tool here too. Hold on one sec. It'll be more obvious when we go back to the 750. Okay. So I got a 750 cutter. I go back over to the program. We simulate it. So we just got double compensation. The control is applying 3/8 of cutter compensation, but the program already applied that 3/8. So we see here, we just overcompensated our system. So we say, okay, well, the reason being is I have a full cutter diameter in there for the tool. I can't do that. Okay, so we go out, we go to our offset table, and the setup would naturally be set the tool diameter to 0. The problem is that renders my simulation unusable because I need the tool diameter there to know what I'm simulating. So now I see that I don't have anything here. I can't see anything. So it's going to affect all of my milling operations. So now all of a sudden the 3D simulation, it's not bringing certainly as much value here because I don't have any tool diameter to represent when I'm machining this model. So how do I get around that if I want to be able to use wear? Well, there is a function, that was actually what I was just commenting out before. So let's put the tool back in. There is a function I can use called TOFFR right here. So TOFFR is tool offset, and then the R stands for radius, or you can put an L in place of the R, and that would be tool offset length. So I can actively write to my radiuses or my lengths in the part program. So in this example, if I type in the field TOFFR equals, and then put negative whatever the radius of the tool that was compensated, so I know right here they were compensated for a 750 diameter tool. If I take away the radius of that tool, and this always has to be radial, even though the offset table is in diametric, this value is always radial, it will then remove the compensation that I just put in from the offset table, but still leave the full diameter there for graphics. So now I can output wear, yet all my simulation is going to be correct because it's not double compensating that tool. This works out really well too when I have common tools that I'm bouncing between shop mill and G-code programs, because if I don't do this functionality, then I have to keep remembering on adding the tool diameter, removing the tool diameter, or I have to have duplicate tools everywhere, because when you go to shop mill, it's going to need that tool radius. So in a scenario like this, if I was compensating for this given tool, I can still increase or decrease the diameter here, the full diameter, or if I want my operators to do that small 10 thou plus, 10 thou minus, you just come over to the wear. Here, actually, I had a value there, but I'll put some other value. And then I could increase or decrease the tool diameter right here under my tool list wear. That will still apply. So that's still a viable compensation. It will still affect my part tolerance. So the TOFFR statement is specifically allowing me to now handle the full cutter diameters at the offset level, even though the compensated path has already accommodated for them. Okay, so let me transition out. Certainly there's a lot more we could go through here, but we do have a couple other topics we want to cover here in our limited time frame. So we're going to go back over to our presentation. And the next thing we're going to do is we're going to now transition to the ISO side of the world. So this certainly won't take as much time because we're going to run the exact same scenario, but I wanted to just show you what it's going to look like if you wanted to start to use ISO or Fanuc style programs at the control. So what you're going to have here is you are going to use a G code to trigger this, and that's what we call G291. Now, it's worth noting that this is not a billable option from Siemens, but not all controls will be set up to support this mode. And the reason being is it's up to the machine tool builder whether he wants to support this ISO mode. Some do, some don't. Some may leverage it on specific models, but not on others. I would suggest if the system doesn't support it and you want to support it, to get a hold of the OEM and see if there's a reason why it wasn't set up for what we like to call commissioned for this mode. They may have a very good reason for it. Some of the 5-axis technology machines, that's where you get to the power of all of our own inherent functions, and they don't want you potentially running it in this mode, really because you're losing all the functionality that is the reason why you bought a Siemens-based control in the first place on that 5-axis machine. So I guess in some respects it makes sense. When you get to a 3-axis machine or even a 4-axis, I don't see it to be as big an issue. A lot of times if it's not supported, it was more oversight by the OEM. But certainly that's how I would explore it. So from here, if I want to turn it back off again, typically depending on how they set up your machine, a lot of times it will automatically switch back on the M30 or a reset statement. But you would use the 290 like you see here to switch back. And you can actually bounce back and forth from ISO mode to R mode, which is also called DIN mode, as much as you want through a part program. So you could have segments of a part program written in ISO mode and segments written in R code and just jump around just by triggering the 290 and 291. You're not limited to the entire length of the program. Now, what happens and how do I first know that my system was set up for ISO mode? Well, the simplest way to look is just go to your offset table and you're looking for an H offset column. As long as the H offset column is there, that means your system was set up to support ISO mode. If it is not there, if you try to use G291, it's going to give you an unrecognized or unsupported command. But as long as the offset column's there, and you'll need it once we get to setting up the offsets, you can then start to use this. Then certainly the other area is the naming of tools. On our side, if your post supports it, we can use named tools. When you get to the ISO mode, since ISO controls only support tools with a number value, you can never use named tools in this mode. So it has to be a T1, T2, T3. There's just no other way around it because we have to comply with the way their controls work. So, we may get a little forgiving and allowing a few commands go through, but fundamentally, say a 90% rule, the way that machine runs is the way we're trying to now make this machine run. Okay, so from there, we're going to jump over to the editor, take a look at a program that was posted straight out of a Fanuc-based post, and you're going to get a chance to see the format, how it looks and compares to that other protocol. Here, we're going to just take a quick look at your normal start statements, normal tool change statements. All this is an exact mimic because there's no editing required. That's the whole point. Really, the only thing you should have to do is handle the G290, G291 trigger. Other than that, this should just drop right in and run. Now, we will be able to support our graphics. We will use the blank function, but I will show you how you can add the workpiece function. That's one of the commands we do allow you to put in, even though it's a Siemens-based command. But normally, standard rule of thumb, I would usually say if their control doesn't support the command, you probably aren't going to be able to put it in the program here while in this mode. And then more importantly, I do want to switch over briefly to the auto side of the world, because here you'll start to see that it's going to look a little bit more unique once you start running the ISO programs. Okay, so if we switch back over to SINUTrain, I have a couple quick programs prepared. So here is our basic G291 CADCAM. So this is the exact same job you saw. In fact, I posted it at the exact same model. I just used a different post to handle it. But you'll see first off the bat, our comments are totally different. Here we're using parentheses as opposed to our semicolons to stipulate comments. You get down into the G code here a little bit. You see a G20. That's inch mode in a Fanuc or an ISO-based program where we are using G70 or 700 on our side. So we're switching over all that compatibility. The normal, rapid, plain, cancel, cutter comp, that's all standard. But your G49, your G80, those things are very specific to ISO controls. So there you see those. Tool chains and tool change protocol. Again, can't use the name, have to use a number here. Come down, obviously our spindle commands, it's all pretty similar stuff between the control platforms. But one of the big things why we need the H column is right here. G43H, a number. So that's how ISO controls call up their tool length offset. They need this G43 command to call it up, where we just drive it right off of the T code command. So because of that, that is why you needed that H column to support this. And then from there, you'll see arc statements. This one happened to have been posted out with standard arcs and radiuses. Actually, a little further down in the program where I get to the helical cutter path, We do IJK, so we support either one. You can bounce between either scenario, so IJK center points or radiuses. And then as you go further down into the program, we'll get over to our drills. Here's our tool 3, and then we get down to the drill, and there you can see there's our G81, our Z-depth, our feed, so it's going to look exact same way. It's the exact same cycle. Give it our coordinates, cancel our drilling cycle, your reference returns, your G28 to stage it, the incremental switch, all that kind of stuff. So we support all that standard protocol. Here's a G83 for a PEC drilling cycle. So if I was to simulate it, you'll see we get into the same scenario we had before originally when we first started playing with the Siemens program. There was nothing here telling it to blank, so it's just going to give me a basic wireframe. I do have the ability of using this blank feature like I showed you earlier. So if you don't want to worry about it, but you do want to get the solid graphics up, we can come in and turn on the blank, and now we'll be able to simulate it just like you saw before, even though it's an ISO program. And then we can do all the normal stuff, rotate it, zoom, whatever we want to do. That's all going to work the same as you guys are used to using. Here's our drilling, tapping, whatever you happen to be doing. But what you can do, there are some commands we will allow you to intermix, and the block form is one of them. So if I wanted to, kind of same rules apply. So stage it just after your work coordinate, but I can go to various, I can drop my blank in. So now my blank is here, right inside of the ISO mode program, and now when we run it, we'll get the blank to simulate for us. So that's okay. That's totally up to you guys if you want to add that to the part program or you just want to trigger it with the blank button. Certainly either is a viable solution. Now, when we want to get to cutter compensation, same rules apply. Kind of everything that we just saw or went through could potentially be a scenario here. This one is one of the ones that was methodized where we weren't using the where feature, but we were using comp at the control. But here you'll see you got your G41. Now they're using a D to call up the tool diameter because they have cutter comp enabled. You still have your G43 H offset up here. And now we can start to simulate it. So you'll be able to run cutter comp, non-cutter comp, doesn't matter. If I was running the where scenario, then I certainly would have a problem because you're not going to use the TOFFR functionality or anything like that. You would be obviously a little more limited there, so to get the graphics up and going. Now, let's jump over to the offset table real quick because I do want to show you some of those unique things that needed to be set up. So when I'm in the tool list, and I have my H column, it's important that I define the H value. And the H value, generally, it doesn't have to be, but typically, the H number is going to match the tool name right here. So H2, tool 2, tool 1, H1. So if for some reason you neglected to fill that out, if you go to try to run this program, whether it be simulation or auto, you are going to get an error message. It's going to tell you, in this case, H number was not defined. So it's calling out the block number. So if I was to jump back to the part program, I see, oh yeah, there we go, N140, and I'm calling out H1, but H1 currently does not exist anywhere. So we come in to find my H1. And then again, just your names. Here you are limited to having to use a number for the given name. You couldn't use the verbal name or explain name. And then from there, obviously, we're not going to support feed per tooth or any of those scenarios. So that's kind of stuff. There's no compensation that certainly that I'm aware of for tool geometries like drilling angles and whatnot. So you wouldn't have any of those functions. So if you had any of these values on the line, they're just going to show you in the picture, but they're not going to really do anything else for you from that scenario. Okay. So once you've defined that up, once we go in, we validate our program. Really the last thing that's there for me to do is to run over into execute. So you're going to jump over into auto mode or execute mode. It loads up into the program memory. It's going to look just like it looked in the editor, and it's going to appear the same scenario. So as I run, I can bring up simultaneous record, just like you're used to when you're working with, the other programs. So all those features are still going to function the same and work the same. Go to maybe a top view here. Do a quick auto zoom. But what I want to show you, more importantly, is what's happening in the background. So if I expand my vertical soft keys over to see the all G-code functions, normally when I'm looking at a machine, a Siemens machine, this is what I would see. I would see a mixture of G-code-based commands and verbal-based commands. So, so certain strategies, diam off, comp off. These are a lot of the, this is kind of like our SUPA statement, if you guys are used to using the SUPA statement for a retract value. These are all our verbal statements in the control. Now watch what happens once we executed or initiated the G291. The system actually switches all the backend commands over too. So if you were to look at the system, it's going to be running all of the same ISO commands that I would be expecting to see on my machine tool. And some of these that aren't being called out from the part program, these are commission-based commands. So it is dependent on how the guy set up your machine. But these are all the structured commands. So as you're running, if I back out, you can see it as it's going through and running this job. Those are the functions that are currently enabled. And then when it gets to the M30, you're going to see that it's going to switch back because it reinstated. I actually had a G290 at the end of that, so it flipped it back. But it would have either way with the M30 and the way this machine happens to be set up. And then I'm back in. Other than that, all the other triggers are going to stay the same. If I happen to be using op stop, let's say, I'm going to turn it on the same way I would have turned it on, just in the regular programming area. Once it gets to that M01, in this case, she's going to pause. So there it hits the M01, she stops, it's telling me I'm either on a program or op stop scenario. Cycle start. You can use block search. Be careful when you're doing the search with calculations. We've added a lot of that function on the later versions of the control, but some of the earlier versions, when you were in the ISO mode, you couldn't do with calculations. That's when the system scans and sets up all the modal commands at the point I'm asking to set it up. So I would be aware of which control I'm using. That's this block search strategy. If I try to use that, probably the safest bet when running in ISO mode, since an ISO control doesn't really support that. If you want to really truly comply with how an ISO control runs, you really shouldn't start unless you're using without calculations. That would be what we would consider a dumb start, where I have to have a safe starting point, right? Tool change or some other point that's going to set up all my modal commands before we get into it. Okay, so that is certainly an overview of 2.5D stuff. Now I would certainly like to kind of spend the rest of our time here getting into a little more advanced functionality. So here what we're going to do is we're going to go over and we're going to talk about a free-form three-dimensional surface. So in this case, this would be what the surface cutter path would look like. It's a three-dimensional geometry. So we're going to come in and I'm going to show you the basic path first. And then what we're going to do is we're going to show you how we have a program methodized to do some roughing and semi-roughing and then finishing it, and how we can handle that and some of the unique things we can do that'll make dealing with these large programs a little simpler, because they do get pretty cumbersome. So certainly we'll come in, we'll take a look at it, same file structure scenarios. If I want to come in and execute it from external sources or edit it and whatnot, it's going to work the same way, dealing with external memory as we're looking at. Now, from the post-processor side, especially when you get to these advanced programs, I think one of the biggest pain points when you deal with post-processors is what we would consider legacy commands. So in the Siemens world, we like to say we're always upwards compatible, but never backwards compatible. So what does that really mean? It means that we are always trying to keep the control kind of at the leading edge of technology. So because of that, we're always adding new functionality to the control to increase the system's performance, give it more functionality. Well, we want to be able to always make sure that the old programs will still run in a newer control. So if you buy a new control from us, you're not going to have to reprogram all your jobs. If you wanted to take the job from your 10-year-old machine and put it in the current machine today, from the Siemens side of the world, it should run. The problem is you're going to start to see these legacy, these older commands, they aren't going to give you the full capabilities of the control. That's okay if you're methodizing the same job because you're used to the performance you were getting out of that job. Where it becomes an issue is this post-processor. This post-processor was written, I don't know, 3, 4, 5 years ago. So the post developer at the time, he did everything he could to make sure he set up this post-processor with the latest and greatest commands, and I'm sure he did a wonderful job. The problem is the post-processor hasn't been touched in 5 years, and now we're going to apply it on a new control, and all of a sudden we're triggering all these old functions, and now we're going, the performance isn't so great. Well, yeah, you're basically tying our hand behind our back, having it run at this older state. So that's where it gets to be a challenge. Do we kind of keep these guys to keep updating the post-processors to support it, or how do we deal with these technology cycles? Like the technology cycle you see on the other side. There's another example, a lack of technology support, because it takes a lot to keep up with us. We come out with new software a lot. We're always trying to push that leading edge. So there are certainly some things that can be done, and adopting a sub-program structure functionality is a simple way to be able to keep the CAM system from having to worry about a lot of those very Siemens-specific functions. Because what you end up doing is you end up having them in a main program, and you can write the main program longhand because it's not a whole lot to it, and then copy and paste it and just rename it to a new name when you're going to do a new job. And then what happens is the sub-program now that you're getting out of the CADCAM system, well, that can be what CADCAM does really well, and that's cutter path strategy. And that's all that has to be in that subprogram is a strategy. You don't even want to have the tool changes in there, just pure cutter path. And then you use the main program structure to then just decide when you want to call up that subprogram, that portion of the job, and execute it. And you can set up all your technology statements, all of your high-speed functionality, all that can be sitting in the main program, and you're not relying on a post that may be outdated to give you these current command structures. So we are going to look at that. There are multiple ways to call up subprograms. The example I showed you, because more commonly, especially when you get the 840 control and bigger files, you may not want all these files to be sitting inside of the NC memory. So I'm going to show you external calls, but you can also have just a straight call. I can just literally type the name of the file, and it'll find wherever that file exists within that directory structure and run it right there. Or you can use external calls once the file exists outside of our NC memory. So we're going to play around with both. From here, we're going to start to use a little bit of advanced functionality. The advanced functionality, I can start to push parameters into the subs. Makes maintaining them real easy. I don't have to be drilling into these subroutines all the time to make editing changes for speeds and feeds and whatnot. So we'll show you a little bit how you can do that. And then you can even use the go-to statements for jumping around. Now, once we do that, we will take a look at our Cycle 832. That's our high-speed roughing cycle, or high-speed machining cycle, shall I say. So we're going to take a peek at that. This is starting to show you some of the different triggers. There's really not a lot when you get to our Cycle 832 as far as what the user has to do. We do really the complex stuff on the back end side. So really all you're going to have to do is tell us what is the operation type. Is it finishing, is it semi-finishing, or is it roughing? What is the chordal or the tolerance that was used out of the CAM system that represents the cutter path? We'll talk about that in a little more in a second. And then if I'm doing a 5-axis job, I can control the orientation angle, the orientation tolerance, shall I say, in business. Other than that, that's it. So potentially 2, maybe 3 variables. That's all you really got to worry about from the operator programmer side. The back end, there's all kinds of things going on. So the system is triggering what we call our compressor. The compressor is a spline interpreter. So what it does is it takes these points that you passed me in the CADCAM system, because a posted program is really just a grid of points that's trying to represent this fluid surface. So what we do is we're kind of reverse engineering. We're taking these points and then transposing a spline through the points to try to figure out what was the original surface when it was designed in CAD in the first place. And then that's what the system runs. And that's where the chordal tolerance comes in. It's really just the deviation, the allowable deviation from the spline to that point. So that's where you want to know what tolerance was used at a CAM system. If you don't, I have some recommendations here you can apply, and it'll get you pretty close. Certainly our look-ahead functionality gets triggered all through Cycle 832. We have jerk limitations, feed-forward controls get turned on. All these advanced functions are getting turned on in the background, but you don't have to worry about it. Now, when you dealt with the legacy command, or our older Cycle 832, you actually had to turn on or tell it which of these functions you wanted to leverage. And we got away from this because more times than not, people would actually just pick the wrong options. And next thing you know, the system, because of that whole backwards or upwards compatibility scenario, people would be picking the wrong functions, and they would be reducing their performance, and they didn't even know it. So if you do have older post-processed programs and it is using the older cycle call, they will run in the newer controls. You can still edit them like you see here with the older format, so how it would look if you opened the older cycle. But really what I have here is just the core recommendations if you are using it. So certainly if you're doing 5-axis, you would want to be using Traore. With the compressor, you would always want to use CompCAD. It's our latest version of the compressor. When it comes to path rounding, in fact, this is an older document. The newer one would actually be all the way up to G645, so you would want to be using that. And feed forward soft. So this would be our core recommendation if you were using these older cycles of a baseline to start from. Now, from there, let me go back one screen here. Bear with me a second. I wanted to show you, I think I had it on the first one. Okay, so one thing I wanted to show you here is a lot of times I have trouble with guys, they're not sure what the chordal tolerance is. So this is a good recommendation or baseline for you. If you don't know what the chordal tolerance is, you should use these as a starting baseline for your numbers. So roughing, if I'm in metric, it's going to be 0.1 millimeter or 4/1000ths of an inch. If I'm semi-finishing, I use 0.05 millimeters or 2/1000ths of an inch. And then if I'm finishing, 0.01 millimeters or 4/10ths. Obviously you can round up or down. This is a baseline. So if, in fact, you don't know, and you can go up or down with these to tighten up the loop or to relax it a little bit, depending on if we really want to get a lot of speed or if we're worried about surface integrity and surface quality. But this would be a good starting point if you don't know what the chordal tolerance is. Sometimes you just don't have that luxury. Okay, so once we look at Cycle 832, we'll then take a quick peek at some of the graphics solutions here and progress on. So we are certainly running later in the hour here, so let's jump over and take a peek. So I have first what I showed you, or I brought in. This is what I would expect to see, just a basic posted file. So this would be have all the technology, have all the, here we're running a roughing scenario. We come in, this would be setting up the Cycle 832. So that's what it looks like, Cycle 832 call. This one happened to have been posted with the program, or it could be inserted in if my post-processor is not supporting that. And you can use this to define, am I roughing, am I semi-finishing, am I finishing? And the way the trigger looks is, a single diamond, I'm only concerned with velocity, speed. If I'm doing a double diamond, I want the best speed I can get, but I don't want to compromise any quality of the product. Or it's kind of like, the old adage, I can have two, never all three. And then I have my finishing scenario where I would be more concerned with accuracy and surface quality than speed or velocity of my surface. So you pick the geometry, you define the tolerance, if I was using a multi-axis program, then I can bring up my orientation tolerance. In this case, I'm not. And then you save it, and it builds it in. Now, a nice little feature when working with these surface files, and it's quick, down, and dirty, is if you hit your double arrow over, we have what we call our mold maker view. And this is going to give you a quick snapshot of what the surface looks like. So it takes almost no time at all, and it's going to give you a nice quick representation based on the cutter path of what this given surface path is going to look like. And then you can hide geometry, different points if you wanted to kind of get a better understanding. But this is just a quick, simple, down and dirty, what we call our mold maker view when you get to 3D surfaces. It'll certainly work on that 2D file I saw, but it's not going to give you as much of a representation. Now, with that being said, as long as my block form's here, I can jump in, we can simulate this type of cutter path, and we can start to run the system. The problem comes in, especially when I'm dealing with larger program files or multiple operations. So this one right now was only posted out to be the finished path. But if this was posted complete, this file would start to get very big on me. And I'd have to deal with, let me shut this off for a second. I'd have to deal with this huge file, finding different tools, different operations. I mean, this file right along, we got almost 10,000 lines of code just for the finish. And this is a small little 4x4 part. So that's where we can start to utilize this subprogram, main program type of logic. So what I did here, I pre-staged this for you just to show you, is I created a simple little main program. I called it my surface main. Normally, I like to keep the main program in my NC memory. They're small. You can see this is 747 bytes. I mean, it's nothing. You could have thousands of them here. But what this does is this surface program, through using functions like external call or just calling up the basic sub, depending on where it is. And the sub can be a main program file. It's okay. But this allows me to then jump out and go grab these different portions of the file. Now, one of the things I like to do is I like to use our R variables. And these are what we call user variables, to then be able to push to these subprograms. So if you look at the first one, I happen to call it op1. That was the name of the file I chose, and that was posted out as the roughing operation. So if I, for argument's sake, just to show you guys what's going to happen here, if I put a end of program real fast, and I simulate it, the system's going to jump out, it's going to grab op1, and op1 was intended to be the basic roughing scenario, and we'll just kick up the speed a little bit, chunk it down. So this would be where I would be coring out the block, getting it prepped for my finishing routine. So here you see she's jumping around. We can turn our path on or off, but I'm just kind of getting the surface pre-stage, pulling out some of the core material. So what I'm doing here is, first of all, if you scroll up, you see I got feeds for op1, spindle speeds for op1, feeds for op2. So I'm using these R variables. And then we do our tool changes here. I set up my cycles here. So this is where I'm not worrying about the CAM system having to know what's the latest cycle 832, or if I'm just discretely writing some of these corner rounding functions or whatnot, velocity cycles. I could have done it right from the part program here. And then I'm figuring out how I want to call up the sub. Now, the way subs work, if they're sitting anywhere within NC memory, specifically in the folder that my main program's in, I don't have to give any type of path statement at all. I can literally just type the name of the file. It would find it and start running it. However, if I want to have my subs externally, whether it be on my local drive, which is where I chose to put it, or maybe sitting on a network or sitting on USB, then I'm going to use that external call statement. So in this case, I have a folder, op1, op2, op3. If I open up the file, we'll see here I'm setting up what my variable is going to do. So all I have to simply do is say S equals R11, and that's setting up that variable 11 is going to set up my spindle speed for this operation, or R10, feed. So F equals R10. So the R10 equals, and the number that I had in the main program is just forcing that number into the feed or into the speed. You see, I don't have any tools, no technology. It's the cutter path. It's the geometry. You know, if I was to look at the mold maker view, I still see that geometry right here. Right? I blocked out geometry, but that's all I'm getting here. And then everything is now handled in that main program. So certainly from an operator standpoint, it makes it really quite simple to be able to manage these things because they don't have to dig through long lines of code. They can just go to that main program. In my case, my main program, I'll go back to it here real fast, was 15 lines of code. Yeah. Going on lines of 10. I mean, not very big. Didn't take me much at all to be able to create it. And that's how we'll start to push into it. So then from there, if I'm doing the external call, I do need to stipulate an EXT statement, external call, then in parentheses, and then in quotations. If it's on the local drive, you'll use the statement local drive. If it's on the USB or somewhere else, this path may change slightly. But this is where you're setting it up. You're telling it what directory to look in, and then you're telling it the physical name of the file you're looking for. Probably one of the trickiest parts is just making sure you get this path exactly right. You know, like see this is subs.dir. Well, that's because my subprogram directory, if we come back over to local drive, this is a dir directory, so I want to make sure I have the correct directory so it finds it. So that's probably the biggest challenge, I think, sometimes when you're first figuring out this functionality is just getting this string right, getting the path right. Because once you have it, then it's just a matter of just changing the folder I'm calling, changing the file name, my structure's there. So you can create this as a template main program and then just keep calling and keep banging it out. Okay, so then from there, this would handle all of its operations. You know, so if I was going to run this real time, we could jump over to execute. Here I'm in the Surface main. Let me turn my op stop off. A lot of times when I'm validating things, especially in Sinutrain here, a lot of times I will like to run them in the auto mode over running it in standard verify. You'll find it'll give you a little better impression and feel of the program. Certainly the surface quality, I think, of the model is a little more real-time to what I would expect to see. So a lot of times I will come in and drive it as if I was running it at the program level. Now, one of the things that's kind of nice, kind of handy to do is using these go-to statements. Because, you know, a lot of times I may want to jump around in this program. Maybe I already roughed it. I stopped it in the middle. So that's where we have just a simple go-to. And then I have an end number. And an end number is just telling you where to point to. So right now, initially, I'm telling you just go to the next line of the program. But maybe I want to jump all the way down to my finish. So I know that I'm going to jump down to, in this case, let's get rid of the M30. I put before. We're going to jump down to the finish, so I'm probably going to want to jump down to at least N115, my tool change, right? Because I got to make sure my 1/4-inch tool is in there. So I tell it, oops, erase my N. 115. All right. So by putting that simple statement here, I can still run the part program from the beginning. See, our block search function works really well. The only problem is if they're very, very long programs, it can take a little while to scan all the way. And a lot of times if I know that I have a safe start point there, I'm not worried about scanning up to it. So the little go-to allows me to just jump over all that stuff and immediately move right over into, in this case, the finish pass. So if I was to reset it, run it again so you see the block. Now we jumped right to the finish pass, same program, just simply using this little go-to as a mechanism to kind of bounce around. Okay, so we've certainly had a lot of content there. Why don't we now transition out? I'd like to take some questions, get some questions for you guys before we wrap it up here. So with that being said, I'm going to shut this down and transition. I saw that we did have a few questions come in before. So you guys have a Q&A panel. If there's specific questions you have, please feel free to just type them in real fast. All right. So I find that if you leave in the tool radius in the tool list for rendering, it looks good. But if you have cutter comp in your program, it could be disastrous unless the zero the radius out. Okay. So really, what he was saying here is that double compensation scenario. So that's where you use showing you the TOFFR statement. That is what's removing the radius again from the part program. Because he's right. You know, a lot of times, as long as the double compensation doesn't look that dramatic, you know, I gave you a big scenario. I was using a 3/4 inch tool. But if it's a small tool, it may look make the graphics a lot better, but you're still getting double compensation, and that's going to obviously directly affect that real program. So just to revisit the statement, so you guys have a chance to record it if you hadn't before. It's TOFFR. So bring it down here. So it's TOFFR. So tool offset radius, that's what it stands for, equals, and in this case, you're always going to want to use negative whatever the radius of that tool is. So in my case, it was 750, I use negative 375. So this way, I get full simulation of the tool, but it's not going to affect my part dimensions. All right. How is inverse time handled for feed rates and variables passed as R variables? So inverse time works the same way in our controls as you would be used to in other controls. So that is going to be a calculated feed rate, and it's based on how far away from the center of rotation of a rotary I'm at. So the problem with using a variable is inverse time's feed rate naturally has to change based on where I am in relation to the radius of that rotary. That's the whole point of inverse time. What you're doing is, instead of driving in inches per minute or feet per revolution, you're saying that, well, instead of being in a linear feed, we want to be more slave to the rotaries. So we're using the distance we are away from center line to compensate our feed rates. So I would say in that scenario, R variables aren't really going to work well for you because you're going to have lots of different feed rates. And you'll notice a program methodized for inverse time, you'll probably have a feed rate on every single line. So in that case, probably not a great application. What I will say, though, and a lot of guys don't realize this, is you do not need to use inverse time in our control. Inverse time was developed for controls that had issues with lag specifically with the rotary axes lagging behind the linear axes. So let's say I was doing an impeller blade, and I'm rolling around an edge, and I'm all of a sudden getting this overshoot or this undershoot where I'm digging into, because there's a reversal of the rotary, I'm digging in. Well, that's a lag issue. It's a lag issue between where the rotary is and where the linear is. In a Siemens control, we control our servo loop time so tight that that issue isn't a problem anymore. So the reality is, if you are running inverse time, I would suggest trying to run the control in just standard. Now, if you do run into issues, you may want to play around with what we call feed groups, because it is dependent on how the builder set up the control, and he may not have set up the appropriate feed groups for that. But you shouldn't need inverse time in the Siemens control. Okay, customers have legacy 840s, yep. And when he used the Cycle832, it said it was going to override his GUD7s. Now, it does not work correctly. Is there a way to put this back to its original data? Well, certainly the GUDs, those stands for Global User Data Variables. The GUDs are part of the archive. If, in fact, Cycle832 did overwrite some GUDs, by reloading an original archive, that will put the system back to the way it was. Why Cycle830 is overriding the GUDs is probably a better question for our hotline, because I've run a lot of legacy controls and I've never seen it do that. That's interesting. Now, there may have been, not knowing who the machine tool builder was, there may have been some custom functionality that, that was applied here at the cycle level. You see, our cycles throughout the control, we have an open architecture control. They have a tendency to be highly modified, especially from advanced builders. So the builder could have been doing something different. So we may need to leverage the builder on that, or certainly you may want to try our hotline. Our hotline is 1-800-879-8079, or you think you can get to them right from our website too. Okay, we have a question. Oh, it looks like it was a DMU 50. So I'm assuming, let me see if that was, yes, it's Tim that was asking the question. So Tim, that would probably be a really good question for DMG to see if they know if their CUST-832 on the older system was writing to global user data, because typically it did not. So, but it would not surprise me. DMG does do a lot of modification on the cycle level. They may have been doing something different there. Robert wrote in, can you explain spline? Explain spline versus cycle 832 motion. Well, actually, cycle 832 motion is a spline. That's what the cycle 832 is doing. If we go back to the slide before, and I'm just going to jump out of the PowerPoint. So cycle 832 is turning on our compressor. Our compressor is initiating splines. Our control actually always runs splines. It's probably one of the biggest differences between our control and the competitive controls on the market today. Standard CNC control, when it interprets its path as a formula, will calculate it as a linear path. We mathematically render everything as a spline. The problem is we developed that because we knew that CAD systems held data as splines, and we figured, you know, what better way to get a great surface quality than to be running the exact surface that CAD knows, which is a spline. The problem is getting people to pass the splines directly is a challenge. So that's why cycle 832 was created. It was created to take these point data and interpret a spline and then run that spline. So cycle 832 is physically running a spline. Now, if you happen to be in a scenario where you have the ability of posting splines directly into the system, you don't need cycle 832. Or at least, shall I say, you don't need the compressor portion of cycle 832 because there's no interpretation needed. You're giving me a spline. Our system can run splines directly, but normally we find typical CADCAM packages can't pass that spline data very easily to us, hence why we developed cycle 832. So hopefully that answers your question. G291 is option at DMG machines. This is why I was specifically saying it's dependent up to the builder and sometimes models. DMG does not like to enable G291, the ISO mode, on 5-axis technology, but they will do it on 3-axis technology machines. So if you look at any of the mill taps released, I think some of the early ones, from the very early ones, may not have had it on just because they had neglected to turn it on, but all of their 3-axis mill taps and 4-axis mill taps come standard from the factory with the ISO mode on. You look at a DMU 50, let's say, a 5-axis technology, and they don't have it on because they would prefer you were running in the Siemens protocol when running 5-axis, and I would have to agree with them on that. So it does depend on the machine you're on when it comes to DMG. Okay, well, here we are. We used all of the hour and a half. I'm going to shut off the recording now.